Hi guys, I'm Hitreshu. Welcome back to my 5th episode of Fun with Electronics. In this series, I am designing a robot arm from the ground up in a detailed tutorial. In my previous video, we were able to design a schematic of our custom 6-axis stepper motor controller. In this episode, we will continue our project and learn how to make footprints of our components for the PCB. So let's get started. To draw proper footprints of our components, we should first understand the details of a PCB. A typical 2-layer PCB has copper on the top and bottom layer over a fiber reinforced plastic substrate. Once we make our PCB, the first step is to use a chemical and etch the PCB tracks so we can make our connections. Holes are then drilled into the PCB wherever we need through-hole components to be placed. The next step is called through-hole plating. This basically deposits copper inside the holes to connect the top and bottom layer of the PCB. We then apply a solder resist paint to the PCB. This paint will cover everything except the pads that we need to solder on. Besides preventing solder from sticking, it also protects the exposed copper tracks from corrosion. Next, the PCB is tin plated. The tin plating will help the solder stick as well as protect the copper pads from corrosion. After that, the component numbers and outlines are printed on a silk screen layer. This is so we know which component to place where and what the physical size will be. That completes our PCB. We now have to place our components and solder them. There are two types of components available. The first type is a through-hole component. This component is put through the PCB and soldered from the other side. The other type of component is a surface mount component. This component is mounted on the surface and soldered on the same surface. Now that we understand what the layers of a typical PCB are, let's start drawing our components. I will create a new PCB library and name it Caramel Robot. Now let's go to the schematic library. Our first component is a 2-pin male connector. I am going to find and search for the datasheet online. This datasheet clearly shows the pin sizes and the distance between the pins. We'll right-click and launch the component wizard. The component wizard helps you quickly use templates of different types of components. I am going to select a resistor template. Since it will have two holes just like our 2-pin connector, this is a through-hole component. We now need to find the diameter of the pin in the datasheet. This says 1.1 mm. So I will enter 1.5 mm in the wizard to give it some extra space. The copper pad size can be about 2.5 mm. So we have a sufficient solder to make a good connection, but not too large. So it takes less space on our PCB. Next, we need to find the distance between the two pins. The datasheet says it is 2.54 mm. I will now name and save the component. The wizard outputs this footprint. Of course, I don't want the silk screen printing to be over the pads, so I'll just delete these and make my own. Now the pads seem to be too close to each other, while the distance is correct. The wizard does a lot of work for us, but we may need to fine-tune the numbers. I will double-click on this pad and change the hole size to 1.3 mm and the copper pad size to 2.2 mm. We'll do the same for the other pad. The purple outline is how far away from the pad we want the solder resist paint to be. The grey area is the copper pad, and the greenish blue center is the actual hole that will be drilled in the PCB. We will go to the top overlay layer and draw the outline of the component, which will be silk screen printed on the PCB. The outline typically is the same size of the component. This will prevent other components from overlapping this component when we do the PCB layout. Next, let's place a 3D body on the component. The 3D body allows us to check if there will be any collisions with the mechanical robot body enclosures. This component body can be drawn as an extrusion. A standoff height of 0.1 mm will accommodate any air gaps between the PCB and the component. I will trace the outline and complete this 3D extrusion. Pressing 3 in Altium changes the view to 3D. We can now see what the component will look like in 3D. Let's now place two cylinders to make up 2 pins on the component. The cylinder height is the pin height from the datasheet. We can change the color of the 3D parts to make them look better in 3D. I will now assign this footprint to the component. Our next component is a 25 MHz crystal. Let's pull up the datasheet again. The dimensions of the component are given here. As you can see, this also has 2 pins, so we will repeat the exact steps of the previous component. Draw the outline. Draw the 3D body. And assign the footprint to the schematic symbol. Our next component is the largest of them all, the SAMD51N19A microcontroller. This looks complicated, but the footprint is simple to draw. Let's load up the datasheet and find the component dimensions. We are looking for the 100-pin TQFP package. I'll start again with the component wizard. This microcontroller is a quad pack, which means that it has pins on all 4 sides. We will enter the pad sizes like before by looking at the datasheet. All pads are rectangular. These dimensions are asking for the pin-to-pin distance and the distance from the center of the corner pin to the center of the other corner pin. Let's find these in the datasheet. The datasheet doesn't clearly show the distance of corner pin centers, so we will just make an assumption here. This screen is asking for the start pin and the direction the pins flow in. The wizard is now asking you about the total number of pins in the horizontal and vertical direction. We'll name the component. The wizard outputs this default component. Since we assumed a dimension for the distance between the corner pins, this distance is obviously wrong. We need 14 mm between the 2 vertical rows of pins. So let's measure and move these pins here. We'll do the same thing for the horizontal pins. Now we just need to measure and center the horizontal and vertical rows. This looks fine. Let's adjust the silk screen outline. We will now place the 3D body. This is how our footprint appears in 3D. Let's save and assign it to the schematic component. See how easy that was. Moving on to the FWE 1500 Wi-Fi module, the same exact procedure as before. Load the datasheet, find the dimensions. This datasheet is actually more helpful. It has the exact solder pad footprint provided, so there is no need to measure anything. We can simply copy these dimensions. Remember that the solder pads are slightly larger than the real pin size because we need space for the solder to stick and hold the pin on the board. The pin 1 is located in the bottom right and the flow of pins is counterclockwise. We have roughly 10 pins on each side, so let's leave this at 10 pins each. We'll name the component. As you can see, the wizard tried its best to help us. While this doesn't match the datasheet at all, it is still a good starting place. Let's start from pin number 1 and work our way around. I will simply keep looking at the dimensions and updating and moving each pad till I get an exact match of the datasheet. We'll move the pins to match the distances. There are no pins on the top, so let's delete all these pins. I'll number the pins to match the datasheet. There is an extra ground pin in the middle of the WinC 1500. We can copy and paste a pad here and change the dimensions as per the datasheet. Let's adjust the outline to match the dimensions of the datasheet. The outline should not touch the pads, so we will just delete and redraw these lines to be between the pads. Remember that the lines are just white paint screen printed on top of the board. If you put paint on the copper pads, the solder won't stick to it, as we do the PCB layout in the next video. Altium will warn us if the paint is too close to the pads. Let's draw the 3D body for this component. Again, the goal here is to get reasonably accurate representation of our component in 3D. This helps us understand the layout in 3D, as well as prevents components from going into each other and into the plastic body. I think that looks pretty similar to the WinC1500. We'll assign the footprint to the schematic symbol. The next component is the 0402 capacitor. This one is very simple. We'll open the datasheet and find the dimensions as before. Capacitor and resistor datasheets are usually combined for a range of products. You will need to match the exact part number in the table to get the dimensions. Also, 0402, 0603, 0805 and other similar footprints are standard. They are named like this to give the dimensions in inches. So 0402 will be 0.04 inches in length and 0.02 inches in width. We'll keep the center to center distance equal to the size of the component, which is 1 mm in this case. The dimensions seem fine, so let's draw our 3D body. And adjust our outline. This is what it looks like in 3D. Let's save and assign it to the schematic component. Now that we have a 0402 footprint done, we can simply assign it to all the 0402 components in our library. Our next component is this 0805 footprint capacitor. This is very similar process to the 0402 capacitor we just completed. Again, I will assign the same footprint to all the 0805 components. Another component with a similar process, the 0603 footprint. Repeating again. We'll assign all 0603 components this footprint. Next, we move on to the DRV8825 footprint. The process for this is similar to the other processors we did before, except that this component is a small outline package. We will select the small outline package in the wizard. The datasheet already has a LAN pattern, which is basically the solder pads pattern. We will copy this exactly. The DRV8825 has some additional thermal requirements. This component will heat up a lot on the PCB and we need to take care of the heat. The center pad is connected to the body of the 8825 and we need to give it maximum surface area to remove the heat. We will be using a heatsink also, but it is important to plan the heating of the components on the PCB. The datasheet is showing us that we need these thermal wires in the PCB. I am going to make this pad really large on the top layer. If I go to this top solder layer, I can see where Altium will prevent the solder resist ink from sticking. We don't want so much copper to be exposed as it will start corroding. We would like to cover all the copper except the heat pad part. For this, I will ask Altium to force complete tenting on top. This will basically allow the entire pad to be covered by the solder resist green paint. But I do want to stop the paint from covering the heat pad area, so I will just draw my own top solder mask pattern on this pad. It would also be cool if I can send some of the heat to the bottom layer. For this, I will create another pad on the bottom layer. I can make this nice and large since the 8825 is actually soldered on the top layer. Let's get rid of these top overlay silk screen lines. To connect the heat from the top to the bottom layer, we need to add wires between them. A wire is simply a small hole that connects different PCB layers. This wire is going to be very small, with a hole of 0.2 mm and a pad size of 0.4 mm. This is given in the datasheet. Again, I will force tenting on the top and the bottom layer because I want the solder resist paint to cover these pads completely. This is okay because we are not going to solder these. The through-hole plating process will fill copper in these holes and connect the top and the bottom layers. I will roughly place these as given in the datasheet. Let's draw our 3D body. This is how our component looks in 3D. You can see the wires connecting the top and bottom layers. We'll draw the outline and draw a circle to indicate pin number 1. This will help us easily identify the first pin to place the component. Let's save and assign it to the 8825 schematic symbol. The next component is this polarized electrolytic capacitor. We will start with the component wizard. This is a through-hole component. This is polarized, which means the plus pin and minus pin are not interchangeable. It is axial, which means it will be mounted vertically on the PCB. Let's name it. And draw a proper outline. We will draw a 3D body as per the dimensions given in the datasheet. We need to mark the silk screen layer to indicate the positive pin because this is a polarized capacitor. We'll assign it to the schematic symbol. Next on the list is this 32.768 kHz crystal. This is the same process as the surface mount capacitors we drew earlier. Moving on to this transistor. Again, the process is similar to earlier. In this case, I'm just going to duplicate a resistor component and start from there. I won't be using the wizard here. We'll look at the datasheet and match the pad sizes and the distances. For components like this transistor, we can move the middle pad slightly behind. This will save some space on our PCB. Also, many transistors come with pins in this formation, so we can easily replace this component with another one without changing the footprint. I'll try to match the approximate shape of the component in the outline. The semicircle will also help us identify pin number 1. We just have a few more components remaining. Let's tackle this terminal header. This is where we will be connecting our 10 ampere power supply, so it needs a proper connection. Now this data sheet is not very clear on the pins. I'm going to make some assumptions here. I already have this part available and know how it looks, so we'll be drawing this footprint from the rear component. As you can see, this is a pretty large component. The outline and 3D model is our only true guideline on the PCB. We can't judge the size of this component simply by looking at the solder pads. Next, we'll take this buzzer. Our last component is a TPS 709 voltage regulator. This is similar to the small outline package we did before. Well, that completes all our components. In this video, we completed the footprints of all our components. In the next video, we're going to start the layout of the PCB. So guys, if you want to follow along with this tutorial, hit the subscribe button and turn on your notifications for further videos I'll be posting. Hit ratio out.